Hi, my name is Ariana, and this is my video lab report for Physics 2212 with Dr. Barron's Lab 3, Magnetic Field of a Bar Magnet. The purpose of this experiment was to observe the relationship between distance and magnetic field by using the distance dependence of magnetic fields and the PHYS law to find the magnetic moment of a bar magnet and then compare it to a computational model. The results of the experiment are that the magnitude of the net magnetic field increases as distance increases. The magnetic moment is 2.85 times 10 to the negative 3 ampere meter squared, and the constant n is negative 3.0878. The B off axis was around 4.8 10 to the negative 8 Tesla. Here are some important background equations. The PHYS law relates magnetic field to current and distance between the source of the field and the observation point. The distance dependence of a magnetic field and the dipole magnetic field equation are derived from the PHYS law and are shown on the screen. The models to this lab are an experimental model and a computational model, where the system is the magnetometer and the surroundings are the bar magnet and the Earth. We assume that the bar magnet is a magnetic dipole in order to apply the PHYS law, and that the Earth and bar magnet are the only things producing a magnetic field. The experiment procedures are as follows. First, use the magnetometer app. Make sure that your phone is aligned with the Earth's magnetic north-south axis and set the magnet bar orthogonal to run east and west to measure the on-axis field using only the X component of the app. Second, identify the magnetic sensor in the smartphone by following the process depicted in the pictures. Third, the on-axis distance from the bar magnet to the magnetometer was found using the ruler for several different magnetic field values. These values were linearized by taking the natural log of each side and then graphed. The results from this step are that n is the slope and ends up being around negative 3, and L and K is the intercept, which ends up being around negative 21.285. The initial conditions for this experiment are the predetermined magnetic field values ranging from 20 microtesla to 220 microtesla. Finally, the off-axis magnetic field of the bar magnet was found by following the procedure described in the slide, and the results for the off-axis field are shown in the table. The off-axis or 45-degree field ends up being around 4.8 times 10 to the negative 8 Tesla. Two things I observed are that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here are the calculations in the experiment. I found the magnetic moment by taking the on-axis magnetic field equation and setting that equal to the magnetic field of a bar equation. Using the constants derived from the graph, mu is solved to be 2.85 times 10 to the negative 3 ampere meter squared. Here are the results of my computational model. The cylinder is the bar magnet, the orange arrows represent the magnetic field on axis, the cyan arrows represent the magnetic field perpendicular to axis, and the magenta arrow represents the magnetic field along the 45-degree axis, using the distance from the table in step 4. Walking through my GlowScript code, first I created the magnet and put in my calculated magnetic moment. I then applied the function for calculating magnetic field and established observation locations along the magnet axis and perpendicular to the magnet axis. In this next portion of the code, I created all the magnetic field arrows and printed the calculated vectors associated. Finally, I used the experimental average value of dperp around 0.192 meters to determine the hypotenuse distance d and calculate the magnetic field at this 45-degree location, creating a magenta arrow to represent this. Comparing the experimental and computational model, one can see the experimental measurement is greater than the computer calculations. Some sources of error that may cause this are other possible sources of magnetic field, since the experiment wasn't conducted in an isolated environment, fluctuation of the magnetometer and adjustments leaving room for human error, and error with accounting for the magnetic field of the Earth. What if you hadn't oriented your experiment to compensate for magnetic north? The measured magnetic fields would be different due to not accounting for magnetic north. The only component that should remain unaffected is the Z component, as the magnet and magnetometer was laid flat on a surface. What if you were to stick two identical magnets together? How would the results differ? Sticking two bar magnets together would result in one stronger bar magnet with a bigger magnetic field contribution. Think about superposition. And the results may have roughly doubled, but remained in the same direction. Thank you.